So Frank Artsenius wrote this book, Spacetime and Stuff, which I feel is enabling. It allows all the rest of us now to say that anything else that we're going to do in philosophy of physics is not about space and time, it's about stuff. And so that's my topic today, the stuff part of space-time and stuff. In particular, I want to talk about how we understand matter in physical theories. And so I want to begin with a sort of basic picture that I think many works in philosophy, or many people working in philosophy of physics, and physicists sort of have in mind with regard to what kinds of options are available for what you might think of as, well, the fancy way of putting it, fundamental ontology of a physical theory, somewhat less fancy way of putting it, how we represent stuff. I mean, how we represent matter in space and time. And so one option, reasonably well understood, is that fundamentally what we've got are particles. And what that's supposed to mean is that matter consists of little bits, what you might think of as atoms or something like that, in a Greek sense, which are localized in space, so they've got a location, sort of more or less compact boundaries, so on. They're persistent in time. They're able to bear properties, so a particle is the sort of thing that can have a mass, it can have a charge, so on. And usually we think of these as things that don't have any internal structure. Now, some people like particles. These days, not so popular. The alternative is something else. So usually physicists and philosophers of physics speak of fields as the alternative to particles, where fields are supposed to be something that's continuously distributed over a region of space. And you'll often see people writing on the problems with particle pictures. So for instance, there's a whole literature on whether or not you can have a theory, a quantum theory of particles, a relativistic quantum theory of particles, and the various theorems that are widely interpreted as showing that you can't do that in the sense that you might have thought you'd be able to, and of course people can argue about that. But whenever someone says we don't have particles, usually what they have in mind is instead what we have are fields. So something that's somehow continuously distributed. Now, what I want to ask, and so I think of myself as sort of in that camp. I like fields, not so much particles. And so I want to ask, though, someone's going to go around saying, well, we've got our fields. Can we spell that out, the sort of vague semi-sentence here, and say what it would mean to claim that matter consists of fields? Now, there's kind of a parenthetical here. I mean, so what I have in mind is to say that, ask what it would mean to say that matter somehow fundamentally consists of fields, that what there is at the bottom are just fields. There are lots of ways in which we might use things that we're going to call fields. I'm going to talk about this quite a bit throughout the talk, to represent matter at some sort of gross or approximate way. But even if you do that, you could do that even if you think ultimately it's particles. What I'm curious about is what we could mean when to say that it's really fields somehow fundamentally. Now, ultimately, anyone who wants to ask this question had better be willing to say something about quantum field theory. I'm going to say very, very little about quantum field theory right now. I'm going to focus mostly on classical field theory, almost exclusively on classical field theory. And the reason, one reason is that I don't really understand quantum field theory. But more importantly, I think part of the reason why I don't understand quantum field theory is because one of the primitive notions in quantum field theory is supposed to be a field. And if I feel as if I don't even understand what a field is classically, I'm going to struggle to understand what a field is in quantum field theory. Okay, so I'm going to talk mostly about classical fields. Let me try to be clear about what I mean by a field in this sort of, at this level of description. So I'm going to give a mathematical definition here, and then I'm going to talk about different ways in which we can take this mathematical definition and give it some physical significance, and then discuss how those different strategies correspond to different possible conceptions of what matter would be like if it consisted of fields. So here's a mathematical definition. We're going to understand a field to be an appropriate, smooth, maybe it doesn't have to be smooth, maybe just continuous, maybe something else. Yeah.
This is I'm a novice to this, but when physicists use field, is it completely different from the algebraic notion?
Unrelated, totally unrelated. Yeah. Yeah.
So you have a definition of a mathematical field. So your idea of a classical field, is it building on to the definition of a mathematical field, or do you take the classical field as basic?
We might want to just save some of this stuff for discussion at the end, if that's all right. We'll just have a presentation first.
Yeah, I don't think I understand that question, but maybe it'll become clear what I'm trying to say, and you can ask it again. Okay, so mathematically, I'm going to understand a field to be some assignment of mathematical objects, maybe real numbers, maybe complex numbers, maybe elements of a vector space, maybe elements of a group, or elements of a field in the algebraic sense, unrelated to this sense of field, to points of space or space-time, or perhaps more generally just to points of a manifold. Now, we use that sort of mathematical object all over the place in physics for many different sorts of representational purposes. What I want to do today is to look at a few of those different things that we do. So first, look at some of the different ways in which fields are actually used in physics, and in some sense, more importantly for my project, try to characterize the different ways in which the physical significance of a field is supposed to be in these different applications. So the idea is, in many cases in physics, what we have is some sort of assignment of mathematical objects to points of something we interpret as space or space-time. We use these for different purposes. In each of these cases, we tend to say something about what the physics of assigning a value to a point is supposed to be. And so I'm going to talk about some of those different strategies. Sometimes these are called strategies for operationalization of a field. And then in each case, what I'm going to do after discussing, let me see if I say this. No. After discussing this a little bit, I'm going to ask, what would it mean with this conception of field and this way of talking about how to assign physical significance to a field, to say that matter fundamentally is like that. Okay, and so to give away the punchline, what I'm ultimately going to argue is that even classically, or perhaps not even, forget the even, just classically, there is no univocal field concept. There are a bunch of different, not just different applications of fields in mathematical sense, but different ways of understanding what it means to assign field values to a point of space or space-time. And that's going to lead to a question, which I'm not going to try to answer, but I'm going to say a little bit about, which is, how are we supposed to understand these different field concepts in quantum field theory? Now, to get a sense of why this matters, one of the ways in which we construct quantum field theories, perhaps the way in which we construct quantum field theories, is to begin with a classical field theory and somehow try to use it to produce a quantum version of the same theory. And if we have a bunch of different things that classically go by the name field, it's not clear that we should interpret all of the quantum things that we produce through that procedure I just described as theories that work in the same way. And yet, as I will suggest at the end, it's very difficult in quantum field theory textbooks to detect the sorts of differences that I'm going to point to in talking about classical fields in the way that we describe quantum fields. So I think that leads to, when philosophers say the word puzzle, they usually have something technical, a certain kind of conception of a puzzle in mind. I don't mean at least a philosophical puzzle. I just mean I think that there are some questions about how quantum field theory is supposed to work that get highlighted by this sort of discussion. And I'd be interested in knowing how to answer those. Okay, so here's what I'm going to do. I'm going to talk about 4 different conceptions of field, and then I'm going to conclude. Okay, so first, the first kind of field that I want to talk about are the sorts of fields that we encounter in continuum mechanics. So this is Euler, the originator of continuum mechanics. Right, so in continuum mechanics, we consider things like fluids. We consider matter, like, you can think about things that you ordinarily wouldn't think of as a fluid, like steel or something like that, is the sort of thing that could be deformed. The way in which we would represent that deformation would usually be with continuum mechanics. The sorts of things that we call fields in this context are things like a mass density field, a charge and charge current density field, momentum density fields, and so on. I'll say more about this in just a moment. Broadly speaking, I take it that these sorts of fields are to be understood as representing what I'm going to call bulk properties of matter. I'm going to call them property density fields, sometimes bulk property fields. One of the things that characterizes these fields is that they often appear in contexts that are what you might call phenomenological. They occur, for instance, when we're talking about fluids, where we're talking about large-scale properties of matter without having to say a whole lot about the details of the underlying matter. So let me say what I mean about that. Suppose we want to talk about some water. Secretly, between friends, we tend to think that water is made up of atoms. We can say more things about what those atoms are made of, but we have a sort of next level down conception of this water is consisting mostly of H2O bouncing around in some way. But the way in which we treat water in, say, hydrodynamics isn't to try to describe these atoms or these molecules of H2O bouncing around. What we do instead is smooth it all out. And we suppose that we can think about how much matter is present by assigning to each point where the fluid is present some number, rho. So rho is a function from points to the real numbers. What this represents is the density of mass at that point. You could think of this as, tracking the number of atoms nearby, but of course, at a point, whether or not an atom is present classically is going to be just true or false. So really what we're trying to do is characterize somehow on average how many atoms there are around. And so what we're doing is saying, well, do you give me some small region of this fluid? I would like to be able to associate a mass with that region. What I'm going to do is I'm going to integrate this field rho over the volume to get a quantity that I can think of as just mass in the ordinary sense, say mass in the sense of a rubber ball or something like that. I could then reconstruct what I meant by rho in the first place by considering the mass associated with various volumes as those volumes go to 0. And so I can understand then the mass density to characterize something about the limiting behavior of how much mass there is in various regions as the regions get smaller and smaller. And so I can characterize the mass of this fluid by assigning a field, right? So to each point assigning a real number, and in that way defining a field in the mathematical sense, where what I understand that field to be telling me is something about, on average, how much stuff there is in various extended volumes. Even though I nonetheless think that actually what's going on here is that we've got a bunch of atoms bouncing around. Okay, so fields of this sort of matter property field comes up not just in 18th century continuum mechanics or modern hydrodynamics. Relativistic fields that we encounter all the time, including in contemporary cosmology, are bulk property density fields of just this sort. So this is Lau, who invented relativistic continuum mechanics. Okay, so here's an example. A relativistic perfect fluid, which we encounter pretty often, is characterized by two parameters. One, a mass density, in just the same sense the mass density I just described, and a pressure density, which when you integrate it doesn't tell you the mass, instead tells you the pressure associated with the region. And this characterizes how the matter is supposed to be interacting with itself. Okay, so really the important thing to note here is that these sorts of fields, including in the relativistic case, including in the case where we think of ourselves as somehow describing, say, the whole universe, and, well, let me put that differently. Including in the case where we're describing the sorts of things that we call matter fields in the context of, say, general relativity, tend to have a phenomenological character, where we tend to be agnostic about what the matter actually consists of. Maybe it's atoms bouncing into each other. Maybe it's the large-scale structure of the universe, and we're talking about the distribution of galaxies. At some level of coarse grading, we can think of ourselves as just smoothing everything out and having a notion of average amount of mass in a region. As I said though before, I'm really interested in the question of what it would mean to say that matter was field-like in some more fundamental sense. And so now let me turn attention and ask whether or not this conception of field, sort of matter density or bulk property density conception of field, could support an autonomous concept of matter, one where what we think we have somehow fundamentally is fields in this sense. And so I think a question immediately comes up. So if we're thinking of fields as representing distributions or densities of properties over space and time, usually we think of properties as the sorts of things that are properties of something. So in this sort of case, what would be a property? What would we be talking about properties of? Now in the phenomenological fluid case, easy answer, we say it's the mass density of the fluid. Right? We have some prior conception that we're talking about this bowl of water, and it's the mass density of the water that is a property of the water that we're trying to describe. But if we're saying fundamentally what there is are fields, that more needs to be said about how that's supposed to go. And so I see two broad kinds of options. One is that we think of these as properties not of, that we think of these as properties of actually the points of space or space-time that the numbers or other mathematical objects are actually associated with. And so the mass density is a value associated with the location at which the value is taken, and not associated with some other independent or prior notion of a thing being located in that place. And option two is that fundamentally, to say that matter consists of fields is to say there is some matter. There's something that's playing the role of the water in the phenomenological case. And these properties are properties of that. So let me describe each of these two in a little bit more detail. This first idea, the idea that matter consists of distributions of properties over regions of space, right? So that fundamentally what we've got are just properties associated with points or regions of space and time, originates with Newton. So it's got a long history. Here's Newton describing in an unpublished manuscript, De Gravitatione. Let us then feign empty spaces scattered through the world, some of which, defined by certain limits, by the divine power becomes impervious to bodies. And it is manifest ex hypothesi that this will oppose the motions of bodies and perhaps reflect them, and will assume all the properties of a corporeal particle, except that it will be immobile. But if we further feign that impenetrability not conserved always in the same part of space, but able to be transferred hither and thither according to certain laws, yet so that the quantity and shape of that impenetrable space are not changed, there will be no property of bodies that does not belong to this. It will be figurate, tangible, and mobile, able to reflect and be reflected, and in any combination of things will no less constitute a part than any other corpuscle. I think it speaks for itself.
If it walks like a duck, then it is a duck. If it walks like a body, then it isn't.
Yeah, so that's part two of the argument. Part one of the argument is if you have nothing but a region of space endowed with duck-like properties, said region will walk and quack like a duck. Okay, so here's Howard Stein explaining this view more clearly than I'm going to be able to, as that exchange probably demonstrated. Newton's answer to the question of what constitutes a body, right, and I'm interpreting this as an option one type answer, is that the qualities that fundamentally constitute a body can be coherently and clearly conceived to exist in, or to have as their logical subject, or the metaphysical support of their being, simply extension, regions or parts of space. In the language of later natural philosophy, the distribution of bodies through space can be described as a kind of field on space. So let's ignore that last bit because it's sort of circular given what I'm saying. The picture is supposed to be, Newton is describing a body as nothing but a region of space with some properties distributed over it. Right? So we, in particular, don't need something as a kind of substrate, say, what Aristotle would have called prime matter, to support those properties. We've just got space and properties assigned to it. So this is an option for how to interpret bulk property type matter, bulk property type field as a kind of fundamental matter. But I want to suggest that there's a little puzzle, maybe in more of the philosophical sense now, for this sort of option. In particular, one of the things that we'd like to explain, one of the things that we seem to encounter in the world, is that properties dynamically tend to hang together. So just to explain what I mean by that, if you've got an electron, and the electron goes over here, the mass of the electron tends to go over here, and the charge of the electron tends to go over here. These are strongly correlated with one another. Now, the particle person is able to easily explain why, when the mass of the electron goes over here, the charge also goes over here. And the reason is, the electron goes over here, and the electron is the thing that carries both of those. It's not clear that the option one person has a similar sort of story in the wings. Because after all, at least the way Newton's conceiving of it, it's the properties that are moving. The regions of space are somehow staying fixed. It's the properties that are moving around. And so there's not a thing other than just the properties that goes over here when the mass goes over here. And so it's not at all clear why when the mass goes over here, you should expect the charge to also go over here. Now, Newton has an answer to this. And indeed, Stein puts a lot of weight on this, which is that what causes the coexistence of the basic qualities, these new or quasi-bodies, as well as the laws of propagation and interaction, which form a part of the essential character of these entities, is just God's action itself. Or, in our neutral paraphrase, this coexistence and these laws are, on this view, the fundamental constitution of corporeal nature. So I think what's intended here is to say, why, when the mass goes over here, does the charge also go over here? It's simply a law of nature that when the mass, so arranged, goes over here, so too does the charge go over here. It's sometimes called a law-constitutive notion of body. Newton himself didn't. A law-constitutive? That bodies are constituted by properties and the laws that govern those properties. Okay, so this is about as far as I'm going to develop this idea. I want to sort of, having stated it, set it aside, I'll come back to it at the very end. Because I do want to say that no matter what else is the case, this isn't going to satisfy us for all of the fields we encounter in classical physics. Let me briefly comment on option 2, though. So option 2, remember, was the idea that when we talk about property density fields, what we're talking about are, in fact, the properties of some underlying continuous matter. So some extended thing whose properties are being described. And I think that the big puzzle, if this is the view that you want to adopt, is to say something more about this underlying entity beyond just it's the thing on which these properties attach, or to which these properties attach. And so in some sense, this is just to say what you've done is kick the ball down the field without actually accomplishing anything. Because if you wanted to say that it's fields in this sense that somehow correspond to matter fundamentally, and what you meant by fields in this sense is that they're properties of some other sort of thing, you haven't really answered the question of you were trying to answer in the first place. What is the sort of thing that we're understanding matter to be fundamentally? Yeah. Let's talk a little metaphysical.
Wouldn't you say, Jim, that it's, that last comment, isn't that because the way you've defined field at the outset of this is a property of space, there's an assignment of a symbol to a space-time point. And so you clearly haven't answered the question, what is the nature of these properties you're assigning to space-time points, if you've not said how the intermediate things attach to space-time points. You've just assigned a symbol to an intermediate thing. Is that sort of what you were getting at in this last comment?
Yeah, I think so. Let me think about that in the back of my head, and maybe easy if I want to. Yeah.
Well, this is a small comment I've got. It seems to me that there's a big formal difference with option 2. If you look at hydrodynamics considered as a not as an effective description, when you suppose you're not an atomist, as you know, up until whenever, many were not. In that case, there is a conception of this infinitesimal point particle of matter that has an identity over time, so that there is a flow field through space. And that is one respectable, formal way that the believer in option 2 says that they're different from option 1.
But that person arguably is re-invoking just a particle notion of matter.
Right, but radically different from, Newton or Lucretius atoms in the void. I mean...
Yeah, certainly. So because they're somehow densely distributed. Yeah, that's right. Although, I would have thought that the option 1 person, would still want to have what they might think of as a velocity density field in order to write down,
if they
need to...
Right, sorry, I was imagining that option 1 had only point particles, but you don't mean that.
I don't mean, no, option 1 you're supposed to just say properties assigned to points of space. Option 2 you're supposed to say there's a thing occupying that space that has these properties but isn't just the space itself. I mean, what I have in mind is really, so what Newton was doing in De Graaf was completely revolutionary in the 17th century. There's this long tradition, beginning with Aristotle, of thinking substance consists of matter formed. And so the idea is matter is some unformed, by itself unintelligible thing, but a thing that you then somehow assign properties to, and that's what forming it is supposed to do for you. And I think before the 17th century, before Newton, it was very difficult to understand what it could mean to have a notion of body that didn't have that prior unintelligible thing. But of course, people also didn't like that it was unintelligible. Even Aristotle thought it was unintelligible. And so option 2 is supposed to be that sort of picture. And then the idea is that if this is our notion of field, we somehow still haven't said anything about the unintelligible matter, and we're stuck back in the same sort of later Aristotelian scholastic puzzles that Newton and Locke hated so much. Okay. Whereas option 1, meanwhile, you presumably would like to say a little bit more about just what those laws are and how those laws are supposed to work in general. I'm going to come back to that. Yeah.
Okay.
maybe you'll come back to what I want to ask. I want to ask you a thing about option 1, the line that you put out about it seeming to be harder to explain why the mass goes with the charge. Because I'm sort of playing a game where I'm thinking, imagine we hadn't had a particle conception of matter, we just had fields. The way that we would explain something like stripping the charge away from something would maybe seem more natural. So we have these two fields, one field the sort of charge-like properties propagated in one way, the mass-like properties did something else. And in fact, in the particle way of reasoning, you have to level down and say, well, actually, no, there's a whole other particle, the electron, that carries the charge. All the times we've stripped away these particles there that way. And the mass was mostly in the other particle, the nucleus, I guess, in this example. So I guess I'm sort of wondering whether, if we've gone through this whole process, starting out with fields, I mean, now we know that there are electrons that have more mass than charge, but I mean, supposing we only have fields to begin with, we not maybe say, there are laws that say sometimes the fields go together, sometimes the fields don't go together, and the properties separate.
Yeah, so that last thing I'm going to come back to, but I think that in fact, in so many cases, the properties don't separate. I mean, you don't talk about electrons, right? You talk about a soccer ball. If you kick it, the colors go and the mass go. And you don't think of yourself as kicking the colors, but somehow it all sort of goes along. Okay, but how we're supposed to understand these laws is something I'm going to come back to. Okay, so let me now describe what I take to be a completely different notion of field in classical physics. So the second class of field encode what I'm going to call geometrical information about space and time. These are things that we encounter in general relativity all of the time, and other so-called metric theories of gravitation, but also arguably fields that we encounter even in classical physics, non-relativistic physics, certainly as it's been sort of reconceived in light of relativity. But I don't think it requires that sort of reconception in order to recognize there being things we can understand as mathematical objects associated with points of space that encode this sort of information in classical physics. So what do I mean by all of this? Well, let's just think about geometry without talking about physics at all yet. Suppose you have a sphere. At each point of the sphere, I mean, in order to make it the sphere in particular, we associate an object, something that we can think of, if you like, as a matrix, although it's probably more properly thought of as a rank 2 tensor. We call it a metric. So at each point, we have some value for this metric. What this metric does is it allows us to say things about directions that you can move along on the sphere. So if you represent a direction on the sphere by an arrow, this metric is going to give you information like how long that arrow is and what the angle is between two arrows, two different directions you can go at a point. It'll give you information like what the, if you have a triangle, it'll give you information about what the sum of the three angles of the triangle are. Of course, if it's the sphere, it's not going to be 180. So the metric is what's encoding all that information. In addition, the metric is encoding information about straightness of line. So if the metric at each point is telling me how long the vector at that point is, I think of the vector as somehow encoding an instantaneous direction of motion. If I associate with the line a vector at each point that I can think of as sort of encoding with how quickly and in what direction that line is going at each point, I can use the metric to give me a notion of length of a line. Now, I don't have a notion of straight line exactly on the sphere, but I have a notion of straightest line, and I have a notion of lengths of lines. The metric, in fact, tells me information about those things. So one, it allows me to say when a line is straight, or as straight as possible on the sphere. It allows me to say what lines are the longest between 2 points on a sphere. And it allows me to distinguish those lines from other lines that, say, squiggle around, and therefore, go between the 2 points, but don't do so in the shortest possible way. Okay, so that's the kind of information encoded by this sort of field, the HAB field. There are other sorts of fields I can define on a sphere that also characterize what I'm going to call geometrical information, albeit somewhat different geometrical information. So here's just an example. Associated with the metric, there's another object that I can think of as a sort of matrix that's not just in 2 dimensions or in 3 dimensions, but somehow is a matrix in 4 dimensions, or a rank 4 tensor, that's going to encode information about how nearby curves that are both as straight as can be tend to diverge or converge as they proceed. And so on a sphere, here's a property of spheres, so you've got two lines beginning at the equator that both point due north, and you just try to make them as straight as you can. They're going to meet each other when you get to the North Pole. That's what we mean, at least mathematically, when we say that the sphere is curved. This object, sometimes called the curvature tensor, encodes that sort of property of nearby curves. Okay, but again, it's a kind of geometrical property that we're going to encode by assigning to each point a mathematical object that tells us locally about how straight lines tend to diverge or converge. All of this is just about geometry. But the point is that an assignment of mathematical objects to points, a field in my mathematical sense, is the sort of thing that we use to describe geometrical information about something like the sphere. Now, we often say, in the context of, say, general relativity, that this is a theory in which we assign to space and time some geometrical properties. And in fact, we use these sorts of fields to represent something about space and time in general relativity. So now I want to ask, what would it mean to say that space-time has a certain geometrical structure? Well, of course, one thing that this means is that we have, as a fundamental object in general relativity, a field, GAB, which is a metric, in the same sense that HAB was when I was describing the sphere. It's the sort of thing that encodes at each point lengths of, say, arrows, or in a somewhat derivative sense, curves. We interpret this to encode information physically about, say, the duration between events as measured by some observer, or distance between events as measured by some observer, angles between curves that pass through a point, relative velocities. It also encodes information about causal structure, so what sorts of events in space and time can influence what other sorts of events in space and time. Okay, so this is a field that's encoding all this kind of information. One of the ways, perhaps, there are sort of two related strategies that you often see for giving physical significance to this sort of field, to somehow saying what it means physically, to say that we have this sort of geometrical field in space-time. One of them uses what you might think of as idealized measuring instruments, like rods and clocks. I'm going to talk mostly about another one that focuses on the behavior of small bodies in the theory, and light rays, so special sorts of solutions to Maxwell's equations. And I'm just going to give one example of how this goes. So one of the things that we use to give physical significance to the metric in general relativity goes by way of what's known as the Geodesic Principle. The Geodesic Principle characterizes motion of small bodies in general relativity. And it says this. It says, free massive test point particles traverse time-like geodesics. A geodesic is one of these locally extremal curves, one of these curves that's as straight as possible through space and time. And so the idea is that in a space that has a metric on it, I get this special class of curves from the metric, the ones that are extremal in the sense that I described on the sphere. This is a principle that associates those geometrically privileged curves with physically privileged curves, namely the trajectories that I associate with particles. So what bodies do in the absence of any motion of force. Now, the geodesic principle, although sometimes presented in pedagogical settings as somehow a fundamental part of the theory, is probably best understood as a theorem of general relativity. So it's something that if you tell me how matter behaves generally, I should be able to derive that in a particular small body limit, it's going to behave in this particular way. Nonetheless, it gives us a way of interpreting the theory. It gives us a way of linking up curves in the mathematical sense with trajectories of bodies. And in that sense, can be thought of as a procedure for giving operational significance or giving physical significance to the claim that we have this field in space-time. We have this metric field in space-time. We can also go the other way. So if you're interested in what else is characterized by assigning a metric to space and time, there's a theorem due to Hermann Weyl, which says that if you have two metrics and they agree on what curves are time-like and null geodesic, so they agree on what the possible trajectory is of massive point particles and the possible trajectories of rays of light are, then they agree up to a constant factor. And so arguably what this is saying is that all of the information encoded in the metric can be reconstructed, in principle at least, just from knowledge of the possible trajectories of small bodies and light rays. And so when I said over here that one thing that the metric tells us is what small bodies and light rays do, it turns out that if you just know what small bodies and light rays do, that gives you the whole metric back. Okay, so
does that require greater than 2 dimensions again?
So you're asking, does it hold in 2 dimensions?
Yeah. Seems like if you.
I don't know. I'm assuming 4 dimensions here. I'd be surprised if it required. I'd be surprised if it didn't hold in 2 dimensions, because it's always the case that if I have all of the geodesics, I get the metric. And so the trick here is that somehow, because I can get a time-like basis, I can get all of the geodesics just from the time-like and null geodesics.
I see.
Good. So this is just a slide that says the thing that I already said. Okay, so here's the point. The physical significance of the metric field and other sort of associated fields that, like the curvature tensor field that we encounter in general relativity that describes space-time geometry, whatever else is the case, these are very different from property density fields. In particular, they don't represent properties of matter. They seem to encode information about how matter evolves. I mean, so the way in which we spell out the physical significance of the metric having a particular value at a point isn't to say, well, it's about the average amount of metrical properties within a region or something like that. We say what it does is it tells us how bodies are going to tend to diverge from one another and move around in that region. Now, at a certain level of abstraction, you can still say what the metric is doing is telling us about properties associated with regions of space or space-time. But I want to say that sort of retreating to that level of abstraction runs the risk of conflating very different ways in which these sorts of mathematical objects can be understood to represent properties. In the one case, we take the thing, we integrate it over a region, and then we understand a property in the ordinary sense of like mass associated with that region. Nothing like that is going to happen with the metric or the curvature tensor. Integrating a curvature tensor or some curvature scalar that you've come up with over a region of space-time, just doesn't seem to give us the sorts of physical information that we want to associate with these sorts of objects. Which isn't to say that we would never do it and that's never interesting. It's just that it doesn't seem to be the sort of thing that somehow the sort of object is encoding. Yeah,
so would these properties be something like propensity to evolve in a certain direction or something like this?
Yeah, so
you don't construe them as properties. So they'd be sort of non-standard.
Yeah. Right.
It sounds like you're envisaging that there's always a unique one of these, like there's only one metric that you have to care about, or only one connection, or whatever. But as far as I can tell, your story would work even if you allow lots of metrics and lots of connections and things like that. Do you agree?
Yeah, I agree with that. Yeah. I mean, so usually you'd want to, probably in that sort of theory, you'd want to say, well, here are some things that track this metric and some things that track this other metric. So the physical significance of metric 1 is it tells you how this class of body move, and physical significance of metric 2 is it tells you fundamentally what the causal structure is, and something like that.
So are you saying these two different roles correspond to bulk versus geometric information?
Yes.
Yeah. And the point is that they're both represented by fields. That's
Yes.
the same as the gadgets.
Yes.
But if you just recognize that there are two different roles, then there's nothing wrong with the first sentence, is there? If you're just clear-headed that there's bulk properties of matter
And geometrical properties.
then it's fine to think that the geometrical properties are regions of space-time. The geometrical information encoded by something like a metrical curvature represents a property of a region of space-time. That'll be all right.
Yeah, that sounds fine to me.
Provided you don't think you're describing a bulk property of matter when you did that.
My worry is just that if you say there's a univocal field concept in classical physics, what a field is an assignment of properties to regions of space-time. You are sort of running over what seems to me to be a very different, an important distinction about how you actually get information out. Yeah.
So would this have any significance on the substantivalist relationist debate? Sort of the information of geometrical fields, you're not treating that as a kind of substance?
I don't think so. So I think that. But I don't mean to say that no one would think so. So for instance, Hartree Field. Forget even about this geometrical stuff. Hartree Field back in the Stone Age argued that if you have fields of any sort in physics, you must be a substantivalist.
Yeah, that's what's coming out for me anyway.
I don't see that at all.
Oh right. Okay.
So I don't see why. So you could be a certain kind of relationist and just say what it means to be a point of space-time is fully exhausted by the possible relations between field values that could be taken at that point. You don't need to have the idea that prior to defining fields, we somehow fixed all the points and they've got some special identity. And so,
So it's undecided, or are you a relationist?
I think that there are actually three views on the table. One of which is substantivalism as it's been described for the last 40 years. One of which is a particularly austere kind of relationism, where what you say is space and time consist of relations between actual things in the world. And one of which is a view where you say space and time consist of relations between all possible things or all possible field configurations. And I think that view is that I don't know of a difference that would make a difference between that view and what you sometimes hear called anti-Hixeitist substantivalism.
Yeah. Okay, thank you.
Okay, so I also think that Newton and Leibniz both held that middle view. And I was trying to clarify their views that we ended up with these two extreme views that look much less appealing to me. Okay, great. We've got two kinds of examples. Now let's turn to the thing that I think everyone would have imagined I'd start with, the electromagnetic field. Okay, so the electromagnetic field, of course, is the basic entity in Maxwell's theory of electromagnetism. Arguably, at least, this is the locus of origin of what we normally call the modern field concept. Certainly, most debates in the 20th century about the concept of field seemed to be about how to understand what Maxwell was doing. We can represent the electromagnetic field, which I'm conceiving of as a physical object here, by a mathematical object, which I'm going to call, which is sometimes called the field strength tensor. So this is a tensor field. Again, you can think of it as a matrix associated with each point that represents roughly how much field is present at a point. This field strength tensor satisfies two differential equations known as Maxwell's equations. We can recover from this sort of ordinary way of thinking about these things relative to a choice of observer, say in Minkowski spacetime. This tensor FAB may be decomposed into an electric field and a magnetic field. And those two fields, if F satisfies these two Maxwell equations, then automatically E and B satisfy the four ordinary Maxwell equations, and vice versa. I mean, so these are just different ways of characterizing the same sorts of things. The nice thing about F is that it doesn't require us to choose an observer or a frame or something like that in Minkowski spacetime, relative to which we write down E and B. So you might remember from undergraduate electromagnetism that E and B have weird transformation properties under relativistic boosts. And so F is something that encodes all of that very nicely. Okay, but what does it mean to say at a point that we have some F? Well, Maxwell had a story. Whoa. Computer is giving me hints. Okay, so Maxwell had a story about this. Maxwell thought there's some stuff, this ethereal substance that fills all of space and time. This is the sort of stuff that can be configured in various ways. In particular, it can have various sorts of oscillatory states, E and B or F. Just tell us stuff about those oscillatory states. Now, we don't think that anymore. This ethereal substance was a casualty of special relativity. But that's okay. We still have a new kind of entity. It's just the electromagnetic field itself. And the field strength tensor, or E and B as vector fields, are supposed to tell us stuff about the configuration of that physical object, the electromagnetic field. This entity, this electromagnetic field, can be associated with various properties. So what sorts of properties? Well, for instance, an electromagnetic field has an associated mass density. It has an associated energy momentum density, and so on. There's more that we can say. So in ordinary electromagnetism textbooks, people tend to say that I can tell you what it means for the electromagnetic field to take a particular value at a point or in a region by telling you what would happen if I had a massive test particle located in that region. Okay, and so what would happen is that it would tend to accelerate, as characterized by the Lorentz force law. A massive point particle with charge to mass ratio k in an electromagnetic field of strength F will accelerate according to this rule, or in other words, this rule. So the acceleration of the particle is going to be equal to k, the charge to mass ratio, times this function of the electric and magnetic fields, where v is the velocity of the particle. Now, the way I've set things up, the electromagnetic field is looking a lot like a nice option 2 type candidate for a field like matter. We say we've got this entity, a fundamentally new kind of thing, the electromagnetic field. It's the sort of thing that we can associate properties with. It's the sort of continuously distributed stuff that can have mass and energy and momentum and so on. And so it's the sort of thing that you might have thought when we said fundamentally matter is field-like. What we had in mind was something like this. It's fundamentally it's the sort of thing that the electromagnetic field is like. But then, when we try to say what just F itself is like, the story we end up telling is one that looks an awful lot like the geometrical structure story. In other words, just as the metric determines a class of privileged curves, the geodesics, an electromagnetic field determines a class of Lorentz force curves, just the curves that happen to be accelerating by precisely the amount dictated by the Lorentz force law. And in fact, just like Weil's theorem, allowed us to go just from the motions of unforced bodies to the metrics, there's a very simple theorem that in the exact same sense allows us to say, if you give me all the Lorentz force curves for just some fixed charge to mass ratio, I can reconstruct, or at least there's a unique Faraday tensor, there's a unique field strength tensor, rather, that gives rise to those accelerations, or to those Lorentz force curves. Okay, so one can say even more about this. In fact, the electromagnetic field strength tensor has the formal properties of a curvature tensor. And I can even think of Lorentz force curves as arising as the geodesics of some metric that's associated with this curvature tensor. And so one can push this geometrical story that really the electromagnetic field is a geometrical sort of field in the sense of the metric and the curvature tensor that I described before, very, very far. Which means that, while on the one hand we might be tempted to say that EM fields are the sorts of things that we were looking for in an option 2 type story, on the other hand, it sounds like they have nothing to do with class 1 fields at all, that really these are geometrical, are encoding information in a geometrical way. Now just to clarify, I don't mean to claim that electromagnetic fields are somehow encoding space-time geometry, the way that the metric is in general relativity. What I mean to say is just that the strategy for giving them physical significance looks very similar to the way in which we give those sorts of fields, the ones that do characterize space-time geometry, significance. And moreover, we can think of them as representing the geometry of other spaces, not space-time itself, but other spaces that we associate with space-time. Let me just mention, because it might not be obvious, although electromagnetic fields can be given in physical significance in this geometrical way and seem like option 2 type matter in the sense that I can associate bulk matter properties with them, the metric, curvature tensor, and so on, it's very difficult, arguably impossible, to come up with notions of mass or energy associated with those sorts of objects that do represent space-time structure. And so the electromagnetic field really does seem to be a kind of intermediate between 1 and 2, because I can't think of these as somehow option 2 type matter in any natural way. Okay, let me turn to my final example. These are fields I'm going to call classical quantum fields. Examples of what I have in mind are Klein-Gordon fields and Dirac fields. And so the idea is, you've got some differential equation. It's named for some famous person in the 20s. You take its solutions. Solutions to that differential equation represent matter of some sort. To say that something is a Klein-Gordon field, this is Klein, Oscar Klein. To say that something is a Klein-Gordon field is just to say it is the sort of assignment of real or complex numbers to each point of space-time that satisfies this differential equation. Similarly for Dirac fields. Dirac. Okay, these sorts of fields are particularly important because these are the sorts of fields, these are the sorts of solutions to these differential equations are the things that we use to construct quantum field theories, or at least many quantum field theories. In particular, it's these sorts of fields that in quantum field theory, these sorts of fields understood classically that we use to construct quantum field theories that we then go on to use to represent ordinary matter, like particles, like electrons and quarks. Right? So these are represented by the quantum version of Dirac fields. Okay, so the quantum version of classical fields that we would understand as just assignments of certain sorts of complex elements of a complex vector space to points of space and time. Now, these sorts of fields, Dirac fields and Klein-Gordon fields, even classically, are easily associated with property density fields. So if you give me a Klein-Gordon field, I can associate with it an I can associate with it a charge current density, I can associate it with it an energy density, a momentum density, a stress energy tensor, I can associate it with it, I guess those are the things I can associate with it. Okay, and so given the role that these things end up playing in quantum field theory, right, so given the fact that it's these things that we end up using to construct our quantum field theory that we use to represent something like electrons, you might have thought that it would be Klein-Gordon fields or Dirac fields, various analogs to those, that are classically going to be the things that we're most able or most naturally going to be able to interpret as fundamental matter fields classically. Moreover, we don't get, in the option 2 sense, I really mean here. Moreover, we don't have this weird feature of electromagnetic fields where when someone then pushes and say, okay, but what does it really mean to say that the electromagnetic field has a value at a point? Just tell me about its mass. Tell me what it means to say the field has a value at a point. And people start telling you about Lorentz force laws. No one does that with Klein-Gordon and Dirac fields. It's not clear that one can do that with Klein-Gordon and Dirac fields. But these aren't the sorts of things that we end up talking about the way that we talk about geometrical fields. We don't talk about how a Dirac field is going to tend to influence charged test matter or uncharged test matter. To the contrary, it's Dirac fields and what you might call charged Klein-Gordon fields that we usually think of as representing the charged test matter that's going to be doing the moving around. But here's the rub. If you wanted to get at some sort of classical conception, field-like conception of fundamental matter, or classical fundamental whatever, Klein-Gordon fields and Dirac fields have no physical significance. In classical physics, they're used in no modeling contexts. There's nothing that you can point to and say, here is the sort of system that I understand a classical Dirac field to represent. Here's how I understand that classical Dirac field to do that representing, and so on. And so it's not just that. So this looked like an advantage. It looked like, oh, finally we were getting away from the geometrical stuff and we can say what we really meant, and it was just matter fields. It turns out that we don't have anything to replace it. There's no alternative story that we tell ourselves about what classically it means to say that a Klein-Gordon field takes a particular value at a point. Okay, so what does it all mean? Let me point to, this is the only exception I know, but this is an important guiding exception to the final claim of the last section. There are no physical applications of classical Klein-Gordon fields. It's still true, technically speaking. But there are other classical scalar fields that are similar in some ways to the Klein-Gordon fields. They aren't solutions to the Klein-Gordon equation. They're solutions to other sorts of differential equations, but seem of a type with Klein-Gordon and Dirac fields, which we encounter in inflationary cosmology. So there are classical models of cosmology in which we introduce inflation, which is supposed to be a period, very early universe in which the universe expands very quickly, where we have something called an inflaton field, which formally looks like a classical Klein-Gordon. Now, the physical significance of positing such a thing isn't often spelled out in any detail. But when I've pressed physicists for, in particular, this line is due to Abbe Ashtekar. Ashtekar argued that the way we're supposed to understand these classical scalar fields, like the inflaton field, is that they're approximating certain features of quantum fields. In particular, they're approximating quantum fields in special states known as coherent states. Coherent states have the following nice property. If you have a quantum field in a so-called coherent state, then the expectation value of its associated energy, momentum, and charge density observables are going to correspond to the classical property density fields that you would associate with a classical solution to the equation that you identify with that coherent state. Now, I don't really want to endorse this. I don't really want to say that I think you can fill in all of the details. But I think that it does suggest a way of thinking about what the classical field is supposed to do. that insofar as this classical field has physical significance in inflationary cosmology, it's because the energy, momentum, and charge current density that I would tend to associate with these fields seems to capture approximately our expectation, the average values for the quantum fields. In other words, the sense in which we end up using Klein-Gordon fields in inflationary cosmology seems to be just that. They allow us to get values for the energy, momentum, and charge current density vectors, right? So, or tensor vector, right? So, in other words, what the fields do is allow us to extract information about bulk properties, and that's the way in which they end up having physical significance.
This scalar field you're discussing, it is the inflaton field.
Yes.
But this is one particular take on it.
Yes.
That instead of saying, oh, it's a new postulated ipso facto, sufficient unto itself field, which we hope to discover, say, oh no, there's this previously identified quantum stuff that gets into special states, and this is described by a classical scalar field in what is today's cosmology, because that is an effective description.
Yes.
So far unknown, detailed, coherent state physics. That's the Hashtacar take.
That's right, because the line wouldn't be that what we have is somehow a new kind of entity that is not going to have some quantum description when you push hard enough. And so the claim is that the way in which we're going to understand this new field isn't ipso facto unto itself, but rather, by appeal to some underlying quantum physics, quantum field theory, that's going to be effectively described by.
So just like perfect fluid in Euler is recognized by the atomist as actually effective on a long length scale compared with the atoms, this scalar field would be a useful effective description.
Yes.
Perhaps at long length scales and low energies of what is actually some crazy quantum.
Yeah, that's right. Now, as I say though, I don't even think that it matters to me to endorse this. It's just a suggestion that really all that we need from something like a classical Klein-Gordon field is what it tells us about its associated energy momentum field and its associated charge current field. And the reason is that on this picture, the right way of understanding what a classical quantum field does is that it coordinates energy, momentum, and charge current properties. In other words, one way of understanding what the classical quantum fields are doing for us is solving this puzzle that the option 1 person perhaps had. So you want to know why does mass go this way when charge goes this way? Well, both mass and charge are algebraic functions of some scalar field. That scalar field satisfies some differential equation. And so that thing evolves in a law-like way. And these two other things, these properties of that field, or these property fields that I associate with that field, also evolve in a law-like way, in such a way that their behavior is systematically correlated, because they're both functions of the same variable. Okay, and so coming back again to the options, right? So option 1 and option 2. Option 1 was the Newton view. Option 2 was the Aristotle view. The story that I just told about classical quantum fields sounds like option 2. It sounds a lot like one of the things that we were tempted to say about the Maxwell field before I mentioned this analogy of geometrical fields. Right? So all that the Klein-Gordon field is doing is telling us, it's the sort of thing that has these properties and then explains why the properties tend to move along together. But in fact, I think that actually what it's doing is it's telling us how option 1 and option 2 can be understood to be closely connected to one another, perhaps even the same. So one way of understanding really what classical quantum fields are doing is that they're the things that allow us to express the laws that allowed Newton to do this law-constitutive conception of matter that he wanted to do in 1680. Okay, so let me try to say this again. The picture is, it looked like we were going to say Klein-Gordon fields are the things that have these properties, and therefore Klein-Gordon fields are somehow the analog to prime matter, or the substrate on which properties attach, or something like that. But in fact, if all we can say about Klein-Gordon fields is that their associated property density fields behave in certain ways, it begins to look like what Klein-Gordon fields are really doing is coordinating these property density fields, coordinating the behavior of these property density fields in such a way that someone like Newton, who wants to say it's just the laws that tell us how the properties move around, can say, well, what these classical quantum fields are doing for us is allowing us to express those laws that then tell us how the properties move around. I mean, you can even think that what it means to say that the Klein-Gordon field has a certain value at a certain point is to say that the associated property fields have the corresponding values at a point. You need to do this in a neighborhood because you need to take their derivative. Okay, so of course, this doesn't quite hold up if we want to apply it for classical electromagnetic fields. They too can be understood to play this coordinating role because we associate energy and momentum density fields with them. But they also still do play this geometrical role with no analog in classical quantum fields. And so, finally, the metric field and its derivatives seem to just be geometrico-dynamical in this way. Which suggests that really now we have three broad classes of classical fields. We have on the one hand fields that characterize and coordinate the distribution of physical properties in space and time, like stress energy tensors. We have fields that characterize geometrical structure and the dynamics of other fields, like metrics. And we have fields that do both. Klein-Gordon fields are now going to be up here. Electromagnetic fields are going to be down here.
In the third option.
In the third option. Okay, so what is this? What are the questions that this leads to? So it seems to me that there are a bunch of questions that one would like to have answered now. So one is, is there some sense in which the differences that I just pointed to, the difference between being in the first option and being in the third option, manifest themselves as the difference in quantum field theory between electromagnetic fields and classical quantum fields? I want to say that there's a sense in which it should, because if you write down the Lagrangians for these theories, the role that the electromagnetic field is playing is the same as in the classical theory. The role that the Klein-Gordon and Dirac fields are playing is different from that role. On the other hand, when we try to canonically quantize these theories, we just ignore this difference. In fact, one way of canonically quantizing electromagnetic fields is to say an electromagnetic field can be thought of as arising from a vector potential which has 4 scalar components. So let's quantize each of those 4 scalar components as if it were a Klein-Gordon field. So you literally just say, I'm going to conceive of the electromagnetic field as consisting of a bunch of coordinated Klein-Gordon fields. And so when I've given this talk before with a lot of particle physicists in the audience, the answer to this seems to be the differences are not manifest, and they shouldn't be. I'm not sure that I understand why they shouldn't be. I think that the reason that one is inclined to say that they shouldn't be is that they aren't, and we think we're doing things more or less right. But on the other hand, we are struggling to come up with a theory of quantum gravity, and it's the fields that represent gravitational degrees of freedom that are purely geometrical in the classical theory, arguably. And so therefore are just the ones that we don't know how to interpret in this coordinating bulk property matter stuff way. Okay. Let me skip that. And 3 is really a repeat of the observation I just made. So electromagnetic fields, other Yang-Mills fields, so what I mean by that are things like the fields that we get in quantum chromodynamics, if we were to understand how they can be given a geometrical interpretation, a la the classical electromagnetic field, would that provide a guide to how to quantize other geometrical fields, ones that can't be given this interpretation like the Klein-Gordon fields, such as symmetric and general relativity? And finally, how are we supposed to understand classical limits here? So, if the classical limit of quantum electrodynamics is supposed to be Maxwell's theory, so just classical electrodynamics, what is the classical limit of a Klein-Gordon field supposed to be? What's the classical limit of a Dirac field supposed to be? So the reason I'm asking this in this way is that if we don't draw a distinction, quantum field theoretically, between Maxwell fields, between electromagnetic fields, and Dirac and Klein-Gordon fields, how is it that failure to draw a distinction at the quantum level is going to end up in the classical limit recovering a distinction? What can we say at the purely quantum level that allows us to say which sorts of fields are going to end up looking like electromagnetic fields in the classical limit and which ones are going to look like the Dirac, Klein-Gordon fields? One thing that sometimes people want to say is that it matters that electromagnetic fields are bosonic, Dirac fields are fermionic. But I think that doesn't answer the question with the Klein-Gordon field. So let me say why. So some people will say, if you have fermionic degrees of freedom, the Pauli exclusion principle tells you that you're not going to get lots and lots of particles occupying the same state, and therefore you're in your classical limit where you have some sort of n goes to infinity and h bar goes to 0 type of limit. You're not going to get a whole bunch of things somehow aggregating in some ground state in a way that's going to reproduce the behavior of a classical field. And so the argument implicitly is that that's how QED gives rise to the electromagnetic field. But it's not at all clear how scalar fields are supposed to work in that way. On the other hand, those people would also argue that maybe we don't have any quantum scalar fields fundamentally. Okay, so let me thank some people. This is Ben Feinstein, Rita Rosenstock, David Mallon.